Thank you very much. First, I want to thank the organizers to organize this wonderful activities, in particular during this hard time. Today, I will report some new results of my groups. We already hear many times about the lattice, so nevertheless, I repeat it, start from the beginning. So in the n-dimensional Euclidean space, assume the A1, A2, An are n linear independent vectors. Then we call the integer and linear combinations of these vectors as a lattice. Okay, it is already well known, so we simply let P be a convex body and X is a discrete set in the Euclidean space. If the P plus X is a tiling of the space, then we call P a translative tiling, translative tail. In particular, if X is a lattice, we call P a lattice tail. Usually it is called parallelohedrons. Tiling is a huge subject. Today, here we only restricted to the translative tiling and the lattice tail. Okay. The lattice tail was started by the Russia crystallographer Fedorov in 1885. He was able to characterize the two-dimensional and the three-dimensional lattice tail. In fact, in more than 100-page papers, he was able to prove this theorem. A two-dimensional lattice tail must be a parallelogram or a central symmetric hexagon. This is simple. In three dimension, a three-dimensional lattice tail must be a parallelotope, a hexagonal prism, a rhombic dodecahedron, elongated dodecahedron, or a truncated octahedra. These are five guys on the right hand here. So this is a complete classification in the two and the three-dimensional case for the lattice tail. In high dimension, the story will be very complicated. In four dimension, now we know there are 42 types of parallelohedron. In the story, Delone and Stokes discovered 51, and many years later, Peter Inger from Bern, Switzerland, was able to discover the other ones. So altogether, there are 42 types. In 5 dimension, there are 110,244 types of parallelohedrons. This means for the lattice tiling. And there was, in fact, the group from Kirati Sriamorn and his cooperator was first classified the dodecahedral Voronoi cell of the 5 lattice. And very recently, the last 2 authors, Gaber and Mark Civino, they was able to prove the Delone conjecture, which imply this is the only possible parallelohedrons, so joined together. The Voronoi conjecture was very, very old, more than 100 years old, which claimed that every parallelohedron is a linear image of the Delone dodecahedral Voronoi cell of a suitable lattice. So this tiling program is also related to the Hilbert's 18th program. As I said, tiling itself is very complicated. And today we only consider the translative tail and the lattice tail. Okay. For the fourfold translative tail, is also the story is complicated. And in 1897, Minkowski first studied this subject, and he was able to prove that a translative tail must be a centrosymmetric convex polytope. Well, it is a polytope, is obvious, but to prove it must be a centrosymmetric one is non-trivial. And furthermore, in fact, for the lattice tail, the structure is very elegant. Here is a technical lemma, technical concept. Let P be an n-dimensional centrosymmetric convex polytope with the centrosymmetric facet. This means not only the polytope itself is centrosymmetric, its facet is also symmetric. So look at here on this picture, the F1 is centrosymmetric, Fi is centrosymmetric, everyone is centrosymmetric. In particular, if the F is n-2 dimensional face of P, like here in 3 dimension, here the F is a segment, here is n-2 dimensional face, then we call the set of all facets of P, each containing 2 translate of F as it is a subfacet, a pair of P. For example, the F1 contain F here and contain a translator here, like that. So the F1 is belong to the build, and this one also, this one. So all together, then turn around, it form a build. Okay, and this then through the work of many famous mathematicians, including Minkowski, Voronoi, Venkov, Alexandrov, and Peter McMullen. Now we know there is an if and only if. So the result joined together is theorem 2. Let P be an n-dimensional convex polytope. Convex body, in fact, is a convex polytope. The following 3 statements are equivalent to each other. First, P is a translative tail. Then the second is P is a centrosymmetric polytope with the centrosymmetric facet such that each build contains 4 or 6 facets, and not more. So you cannot construct a complicated one more than 6. And if satisfy this condition, they also satisfy the third one. P is a lattice tail. So the translative tail, it must be a lattice tail and must have such a special structure. Okay, this is a very fundamental and elegant result. And I have to remark this result, every translative tail must be a lattice tail. First was proved by Venkov, but many years later, as I remember, it was 1980 around. Peter McMullen published a new proof, and then afterwards he was told that Venkov already proved this many years ago. Okay, so that was the one-fold tiling. Then we turn to the multiple tiling. Let P be a convex body and X be a discrete multisite. This means the point can be repeated in the n-dimensional Euclidean space. If P plus X is both a k-fold packing and a k-fold covering in the Euclidean space, then we call P plus X a k-fold tiling and call the polytope a k-fold translative tail. In particular, if the discrete set, the translative set, is a lattice, then we call the polytope K-fold lattice tail. So this intuitively, this is very well. In fact, this is very simple to imagine. The boundary makes some trouble, except the boundary in the space. Every point was exactly covered by K copy. Then we get the K-fold. In particular, the ordinary tiling is a one-fold. Okay, and this is a natural generalization of the one-fold tiling, and it was started by Fedorov in 1936. I wanted to remark that Fedorov was a professor of University of Vienna, and he was at that time he generalized this concept to multiple tiling, since he studied and proved a result of Minkowski on the cubic tiling. Okay. Afterwards, this generalization was started by several very well-known mathematicians, including Hayos from Hungary, Robinson from America, and some modern time, many others, including the Senior Robinson and several others. Okay, but nevertheless, multiple tiling is not as natural as the one-fold. Okay, in 2012, Robinson and his co-authors studied the multiple tiling. In his paper, at the end of his paper, they discovered one very interesting example. This picture here. This is an octagon. As I said, the one-fold tiling is parallelogram and the central symmetric hexagon. Of course, the number of the edge is always an even number. And then the first candidate of the troublemaker will be the octagon. So this may be the Robinson and his co-authors try to consider this one. And in their papers, they discovered that this guy can form a sevenfold tiling, okay? So from the one-fold suddenly jump to the sevenfold, okay? And at the end of his paper, they ask several questions, in particular these two, at least here. He said, compare with the one-fold tiling, in particular the Venkov and McMullen conditions, and they wanted to get an if and only if characterization for this K-fold. To be honest, I myself are not so optimistic for this one, since when the multiplicity is a little bit larger, there were some troublemakers. And the second question is classify the combinatorial type of whole polytope which K-tail the Euclidean space by translations. Okay, so recent years, I worked together with several of my former students. We get some result in this type. In particular, in the plan, we were able to prove this theorem. In the plan, beside the parallelogram and the central symmetric hexagon, there is no other two-fold, three-fold, and four-fold translative tail. This means as Fedorov discovered, the parallelogram and the central symmetric hexagon can form a one-fold tiling. Then you can just step together form the twofold, threefold, and so on. But this we regard it as the trivial ones. So beside this one, there are no other candidate can form twofold, threefold, and fourfold. But there are fivefold. There, in fact, we can characterize all these fivefold translative tail. There are parallelogram, hexagon, and three class of, in fact, there are two class of octagon and one class of dodecahedron with 10 edges, okay? And for the sixth fold, we was not able to classify, but we was able to classify the six-fold lattice tail. So if we put the extra restriction, we can classify it further. So up to now, we know the 2, 3, 4, 5 fold multiple tiling, multiple translative tile, and plus 6-fold lattice tail in the plan. Okay, and then the proof, in fact, is relatively technical. And as one can emergence, we have to work on at the vertex. So we introduce a concept with the name adjacent well. Also I use the colorful picture here. Maybe it's still very confusing for you to see it. We look at the vertex V here. This is our working point, and we start from the P plus X1. If we work it here, if they are joined together very properly and form a k-fold tiling, this means very even at every point. So they have to have a second one, the P plus X2, this yellow one, then join very properly here and turn around with this one, with the first one. And then we have to get a third one, like this purple one here, that join this edge here very nicely. Sometimes, of course, we can, the maybe is in the middle point, in the interior point of an edge, but that nevertheless, in that case, we can always start from one and then join together, turn around at the end. They will join to, well, here is the first one, then the last one, the P plus X8, this read one, join at the end of this edge. This means they are at around this point, they have to, at the end, to form a 2KP. This means that the angle is joined properly. Then this is a very important observation. Then we introduce to the multiplicity at this vertex point, and then the interior point produce a formula, and then at the end to get over to get the two-dimensional case. Okay. And after the two-dimensional case, we work on the three-dimensional case for a long time, and we made some mistake. And then at the end, we read the work of Robinson and his colleague. Once again, we are very lucky to catch the three-dimensional case, since the three-dimensional case, the multiple tiling must be a sonotope, which was proved by Robinson and his colleague. So let P be an n-dimensional convex polytope. We call it a sonotope if it is a Minkowski sum of finite number of segments. In other words, if P equal to S1 plus S2 plus XW, where SI are segment. So the sonotope is a very particular polytope, which are very important in the discrete, in the polytope. And clearly, the sonotope are central symmetric. In fact, every face of the sonotope is central symmetric as well, since it is such a Minkowski sum, that every face must be also such a sum, okay? This is the work I mentioned. We repeat it again. In 2012, Graven, Robbins, and sorry, I cannot pronounce the name properly. They studied the multiple tiling in the general dimension and discovered the following theorem. So, n-dimensional k-fold translative tail is a central symmetric polytope with the central symmetric facet. This means not only the polytope itself is central symmetric, also the facet. So when the facet is in central symmetric in 3 dimensions, in particular can deduce the 3-dimensional k-fold translative tail must be a sonotope. But in 4 dimensions or higher, this is no longer true. There are counterexamples. So assume that P plus X is a k-fold translative tail in the 3 dimensions. From now on, we only deal with the 3-dimensional case, okay? I just wanted to show a little bit the idea. And assume that E is an edge of the B. BE is a build of the polytope determined by this edge, which has 2 times m facet. This number is important, 2 times m. Later on, we will work on this m. So assume the V is a proper point of the edge. This means there are some exceptions, but only finite number of exceptions. So we pick up the point V, which is on the edge. We can imagine, since this is a sonotope, we look at the interior point of the edge. Then if it is a k-fold translative tail, all this translate must be joined properly at this point, just like the 2-dimensional case. Why the sonotope work here? Since we need to use the projections. When we projection to one directions, then the adjacent well, the 3-dimensional dodecahedral adjacent well is the same as the 2-dimensional case. That is the idea. So as the 2-dimensional case, this is the dodecahedral angle, the alpha ij is the dodecahedral angle, then produce it to the plane, which is perpendicular to the edge, then joined together is a multiplicity of the 2p. So at the V point, we can introduce such this rough p is the multiplicity caused at the vertex point, at the edge point, okay? And at the same time, the V is also possible is the interior of some translate. So we can count it the V here. Then the multiplicity, the tiling multiplicity K is the sum of these two. This is a very important observation, and one can prove very easily. But this play a very important role here. So when we introduce this dodecahedral adjacent well and do the projections like here, recall the P plus X is a k-fold tiling, E is the edge of the P, the B E is a build with the 2 times M facet, this as I emphasize here. Then we first projection this polytope together the whole distance and along the E direction to the XY plane. Here we of course assume the E is perpendicular to the XY plane. Since this is an invariant and the linear transformation, of course, we can assume the E is perpendicular to the XY plane. When project it, then we produce to the adjacent well for at the two dimension. Okay, but why we here that in the 3-dimensional it work the projection, since we have to take care to prove projection, we produce the result, but this result can pull back only with the guarantee that the polytope is an sonotope. Otherwise, we cannot pull back. And that is why only 3-dimensional work. And with these preparations, we can prove this very complicated technical lemmas. This means if M equal to 4, this means the number of the M, as I explained, M is half of the number of the facet in a build. So if M is equal to 4, then the multiplicity must be larger or equal to 5. And if the M is equal to 5, then the multiplicity also must be larger than or equal to 5. And when the M is 6, the multiplicity become larger, is at least 6. And when M is equal to 7, the multiplicity is also at least 6. Whenever the M is larger than 8, then the multiplicity is at least 7. This means when the build, the number of the facet in the build is very big, then we do not need to worry about it. The proof of this technical lemma is, as I said before, we start with 1, like here, the black one, the P14 plus X1, then just do as before, the turn around and consider many combinatorial possibilities. And some of the lemma was very long, very complicated, but anyway, they are only finite number. The number is not so big, not so bad. We do not need to use computer, only to use the hand is okay. But anyway, we was able to prove this 5 technical lemma. Then look at here. So if the multiplicity all here is larger than 5, when the M is more than 4. This means if the multiplicity is less than 5, less than 5, this means 4, 3, 2, then the M must be only have 2 possibility, 3 or 2. This means the projection is a parallelogram or asymptotic symmetric hexagons. Okay, so now we can pull back to use the result of Venkov and McMullen, this if and only if one here. Yeah, we have to pull back to use this result, and then we can conclude. So we can conclude in 3-dimensional, in our ordinary Euclidean space, every 2, 3, or 4-fold translative tail is a lattice tail. This means a parallelohedron. In other words, every three-dimensional 2, 3, or 4-fold translative tail must be a parallelotope, a hexagonal prism, a rhombic dodecahedra, a elongated dodecahedra, or a truncated octahedra. This was, in fact, the 5 guys discovered by Fedorov more than 100 years ago. So if even we not only consider the 2, 3, or 4 for the lattice tail, the translative tail also force to back to this 5 possibility. And if try to, like the plane case, if we try to classify the 5-fold, then we get some result, but was not able to succeed. So for the 5-fold translative tail, every build of the 5-fold translative tail in 3 dimensions has at most 10 facets. This already made troubles. So this means it can be 5 with 4, 6, 8, or 10 facets. In particular, we have such an example like these purple ones. This is a cylinder with the base is octagon, and we can also produce dodecahedrons. And then this guy can form a 5-fold tiling, which is not a parallelohedrons in 3-dimensional case. Okay. For the 6-fold one, we also can produce some upper bound, which says every build of 6-fold translative tail in the 3 dimension has at most 14 facets. This means the possibility is not so big, but nevertheless, there are so many geometry and combinatorial possibilities. Up to now, we was not able to classify the 3-dimensional case. Okay. So anyway, up to now, we get some result. So our result provide answers for Graven, Robinson, and Sherwood's questions in the correspondent cases. So we also this partial result seems that the first question of Robinson and his co-authors seems rather too ambitious. I mean, in my opinion, I think it is almost impossible to get a clean-cut answers for their first questions. But for the second questions, we can case by case to get some. Okay, and also, as I already emphasized several times, we was successful in 2 dimensions and 3 dimensions, and for high dimension, it is impossible, since it is very well known in 4 dimensions, the Dirichlet Voronoi cell of the D4 lattice is not a sonotope, since some of it is 2-dimensional face triangles. This means we cannot use the sonotope idea to use the projection and so on, and to go in this direction. Therefore, this method, the sonotope method, cannot be extended to high dimensions. Okay, I stop here, and thank you very much. Here is the reference.